Okay, today we're going to start Unit 8, which is thermochemistry. And in thermochemistry, we're talking about heat. So heat absorbed, heat lost. Sometimes it could be just a phase change like melting an ice cube. Sometimes we could be talking about a combustion reaction, something exploding, something giving off a bunch of heat. So the first thing we need to do is to define what we mean by energy. So energy is defined in science or in chemistry as the ability to do work. So that energy can take a lot of different forms. We're going to be focusing on thermal energy or heat today. So energy can be measured in two different forms. You're probably used to hearing about calories, but it can also be measured in joules. And joules are really small. 1 calorie is actually equal to 4.18 joules. And if you're thinking about food calories, then food calories are actually much, much larger than calories. Food calories are written with a capital C. And so what they actually mean on the back of a package, if it says 200 calories, if it has a capital C, which it pretty much always does on a food package, that actually means 200 kilocalories, or kcal, which means 200,000 little c calories. And so the reason I mention that is because it tells you just how small a joule is. Because a joule, 4.18 joules would be equal to 1 of these little c calories. So, in a bag of chips that has 200 big C calories, it would contain, literally hundreds of thousands of joules. Okay, so joules are a really small unit for measuring heat. Okay, so what is heat? Heat is a form of energy, sometimes called thermal energy, and it's always going to be transferred from hot objects to cold ones, so higher temperature to lower temperature until they're the same temperature, right? So heat conduction occurs when higher temperature, faster moving particles bump into slower temperature particles, transferring their kinetic energy. So we kind of talked about kinetic energy with gases, but kinetic energy is just energy of motion. So if I have a hot cup of coffee, inside of that coffee mug, I've got, essentially water that's got a lot of kinetic energy because it's at a high temperature. So it's moving really fast. When those water molecules bump into the side of the coffee mug, well, the coffee mug is made up of a bunch of atoms, all nice and neatly lined up, and they're just vibrating back and forth because it's a solid, and they're a little bit cooler, so they're moving slower. But when the hot water molecule bumps into them, it transfers some of its kinetic energy, and that causes these guys to start vibrating a little faster. And then when you have air, like let's say you've got some oxygen molecules out here on the outside of the coffee mug, and it bounces against the coffee mug, it's going to pick up some of that kinetic energy. And that kinetic energy started here with our hot water molecule that was moving really fast. And essentially it's like a domino effect. It just transferred its energy to the adjacent coffee mug atoms, which in turn transferred some of their kinetic energy to the air outside the coffee mug. And eventually, if I leave this hot coffee mug out on the table in the room, it will just reach equilibrium, meaning it will be the same temperature as the rest of the room, right? It'll cool down to room temperature. That's the natural direction of flow. It always works that way. From high temperature, heat flows from high temperature objects to low temperature objects. Okay, so then we have to talk about doing some calculation with this. I'm actually going to ignore this little section. I just realized that I copied it twice. So we're going to come down here where it says Q equals C times M times delta T. And those definitions are up above, so you could copy from up above. But what is Q? Q in this equation is the heat gained or lost measured in joules. So if I wanted to know how much heat was lost by my 100 milliliters of hot coffee as it cooled off, I could calculate that, and it would be calculated in joules. The next part of the equation, C, that's a unique variable that we haven't seen before. That is called specific heat okay? And specific heat just means the resistance to change in temperature, all right? It's measured in joules per gram times kelvins, or you can also actually measure it in joules per gram times degrees Celsius, and we'll get into why both of those are okay in this case. But basically, it's how resistant is something to changing temperature. So let's take a look at some examples over here on this table. Liquid water is a great example of something that is very resistant to change in temperature. It has a specific heat of 4.18. So that means that if you have a gram of water, which is about a milliliter, it would take 4.18 joules to raise that gram of water by 1 degree Celsius. Okay? So that tells you that water is very resistant to temperature change. Unlike, let's say gold, which has a much lower specific heat. So if you hold a piece of gold in your hand, it's going to feel cold. And it's going to feel cold not because it is very cold, but because it has the ability to quickly absorb heat from your hand and change temperature. Okay? Whereas graphite, which is a little bit higher, is a little bit less so. It's not going to absorb heat quite as easily from your skin or from its surroundings. So that is specific heat. The high specific heat of water is a very, very important thing to remember. It makes water a really great heat sink. It means that water can absorb a lot of heat. It's why it's so good at putting out fires. If you have a fire in a building and the fire department comes and sprays a ton of water on it, you're not smothering the fire with that water. What you're doing is you're adding enough water to absorb enough heat because once you've removed enough heat, the fire can't sustain itself. So water is really good at absorbing heat. It's the reason that an increase in ocean temperatures of just 1 degree Celsius is a big, big deal, because the ocean, being made up of water, is able to store tons and tons of heat. Many, many, many trillions of joules of heat are stored in the ocean. And so when the temperature goes up, that means there's a lot of heat that's been absorbed by that water, and it's got to be released at some point, maybe in the form of a hurricane or something like that. Okay, M, very simple. That's, of course, mass. So the larger an object is, the more joules of heat it will take to warm up. And then delta T, when you see that triangle, it means the Greek letter delta, and that's just looking at change in temperature. Okay, so we're going to look at some problems and talk about how to use this equation. Let's start with how much heat is needed to raise the temperature of 1,200 grams of water in a pot from 22 degrees Celsius to 100 degrees Celsius in order to begin boiling it. So if it says how much heat, which letter, which variable are we talking about? So hopefully you said Q, right? Heat is Q in our equation, right? So we have Q equals C times M times delta T. And in this case, it's asking us to solve for Q, so we don't have to rearrange the equation, right? All right, and then what do we think 1,200 grams would be? All right, that's going to be your mass, right? And then this 22 to 100, that's a temperature change. So it looks like we're going up by about 78 degrees. So that's our delta T. And then the only thing we're not given in the problem is the specific heat, but that's because it's a constant, so we can find it right here on our table. And since we're talking about liquid water in this problem, that is 4.18. So this one is just a matter of plugging everything in. So we already said that specific heat for water is 4.18 joules over grams times degrees Celsius. The mass in this case is 1,200 grams. And the delta T is just the bigger temperature minus the smaller temperature. So 100 minus 22 would give us 78 degrees Celsius. And now we are ready to calculate. So in this case, just multiplication, 4.18 times 1,200 times 78. And it gives me 391,248. And if I look at the units here, we can see that degrees Celsius cancels and grams cancels, and that would leave me with the unit joules. Now we do want to round for sig figs, and it looks like we only have 2 in the number 1,200 grams. So I'm going to round that to 390,000 joules as my final answer. All right, let's take a look at another one. This is a 28.5 gram sample of an unknown substance. Increases in temperature from 42.3 degrees Celsius to 87.7 upon adding 909.3 joules of heat. Find the specific heat of the material. Okay, so what are we trying to solve for? So find the specific heat, right? And since it's unknown, it's not on the chart, so we're going to have to calculate it. So how do we rearrange this equation to get C, which is specific heat, by itself? Okay, hopefully you said that we would divide both sides by m times delta T to get C by itself, right? So C equals Q over m times delta T. And now it's just a matter of recognizing what everything is. Q, remember, is heat measured in joules. So that's going to be 909.3. Mass is 28.5 grams. And then our change in temperature is 87.7 minus 42.3 degrees Celsius. So go ahead and do that calculation and see what you come up with. All right, there we go. I got 0.703. And that doesn't exactly match any of the values on our table, but it's pretty darn close. If we look at, I think graphite is like 0.70, yeah, 0.709. So this might be graphite, or it might just be a substance that's not on the table. Okay. All right, let's go ahead and try example 3. Go ahead and set it up. See if you can rearrange the equation to get mass by itself. Start there. Okay. So hopefully you said m equals q over c times delta t. I just divided both sides by c times delta t so that m would be by itself. All right, now let's see if we can find all these values. So find q, find delta t in the problem, and find c using the table, because remember it's a copper pot. So go ahead and fill those numbers in. Okay, so there's my setup. 86,000 joules is my Q. The difference here, whatever this is, 84.1 maybe degrees Celsius. As long as I put it in parentheses, I can just put it in my calculator all in one shot though if I want to. And then here's my specific heat. The specific heat, 0.385, of course, I got from the table, right? Here's copper, 0.385, right? So there we go. And then let's see what this gives us. Go ahead and calculate it. All right, and there you can see my answer. I got mass equals 2,656, which I'm going to round to 2 sig figs because my joules only had 2 sig figs. And there is my answer.